Welcome back to the deep dive. Today we were strapping in for the ultimate detour into the land of extreme efficiency. We're going to these places where high-level languages, like Python and JavaScript, they rarely let us even peek. We are investigating a fundamental, user-defined type that is practically defined by a single, ruthless trade-off: efficiency over safety.
This dive is truly foundational. When we program in modern environments, the compiler and the runtime, they handle so much for us, all that resource management. It makes gigabytes of RAM feel cheap, infinite even. But our source material today, it really pulls back the curtain on a design philosophy from an era where every single byte was precious. We're decoding union types.
That's right. When most people hear user-defined data type, they immediately think of structures or structs, the standard way we bundle related information together. But union types they're different. They represent a very specialized, almost surgical instrument in the programmer's toolkit.
And our mission, really, is to synthesize the definition, the complex mechanism, and the very specific applications of this type, which is explicitly borrowed from the C language. We want you to understand not just what a union does, but why a programmer would ever choose to subject themselves to its limitations.
The entire concept, as you noted, it all hinges on one core insight, doesn't it? It's this deliberate, almost aggressive pursuit of memory efficiency.
It's the ultimate compromise. A union is a way of explicitly telling the compiler, look, I need to store one of these many data types, but I promise I will never need to store more than one at the same time. The core function is to allow multiple purposes to share the same allocated block of memory. And this mechanism and all the constraints it imposes, that's the heart of our deep dive.
Okay, let's unpack this and start with the raw definition. Our sources state that a union type is a user-defined type that allows you to store different data types in the same memory location. And that's where the comparison to a standard structure, or a struct, becomes so crucial.
Indeed. Yeah, think about how a standard structure works. If you define a struct with, say, 4 members, an integer, a character, a Boolean, and a float, the compiler has to calculate the total memory needed. It does that by adding up the size of all 4 of those individual members. It's an additive model. You get 4 separate storage boxes, basically, even if 3 of them are empty at any given time.
But the union is the complete opposite. It looks at all the potential members you've defined. It finds the one that requires the largest amount of memory, let's say a 64-bit floating point number.
Yeah.
And then the union itself only allocates that single 64-bit block.
Yeah.
Every other member, no matter its type, is forced to use or overlay that exact same physical space.
That is the critical distinction, and it immediately explains its historical context. What's so fascinating here is that this type is explicitly borrowed from C. C was designed for efficiency, rooted in this highly efficient low-level programming where hardware resources were just so severely constrained.
Right, we're talking about an era where computers might have had 4 or 8 kilobytes of RAM. And that's kilobytes, not gigabytes. You just couldn't afford to waste space by allocating separate memory for 5 variables if you only ever needed one of them active at any moment.
That C heritage is everything. Unions were born out of pure necessity, a genuine need to be close to the hardware and maximize control over every single resource. They are a perfect manifestation of the philosophy that the programmer knows best, even if it introduces, a significant amount of complexity.
So if the benefit is this superior space utilization, using one piece of storage for multiple things, why don't modern languages adopt this more broadly? If it saves so much space, surely that's still relevant.
Well, that is the essential trade-off. The reason modern languages shy away is the immense complexity it puts on the programmer. You gain memory efficiency, sure, but you sacrifice safety and readability. You, the programmer, become responsible for tracking which data type currently lives in that shared space. And if you forget which one you stored last, that's where things get really dangerous.
It's the ultimate aha moment in resource management, but it comes with this terrifying asterisk. You are making a definitive decision. I need this space-saving mechanism, but you're also signing a contract promising to never, ever make a mistake about what's in there.
Now let's look at the mechanics, because defining and using a union type is syntactically very similar to a struct. If you were looking at code, you might see something like union payload, message ID, float temperature reading, both members are listed, and you access them using the standard dot operator.
And that structural similarity is where the confusion starts, right?
Yeah.
Especially for a new developer. Visually, they look like containers for multiple variables, but functionally they are not.
Exactly. We have to stress the functional difference. The difference isn't in how you access it in the code, but in the execution, the memory strategy, and the critical rule that governs its very existence.
Okay, here's where it gets really interesting in this. This defines the entire utility and the risk of the union. Although it's defined with many members, the critical, unbreakable rule is that only one member will be active and valid at a time.
This singular active member rule is the core contract. Let's go back to our example. If you assign the temperature reading, which is a float, a value, and then you immediately try to read the message, the integer. You aren't reading some original integer you stored earlier. You're reading the exact same sequence of bits that was just formatted as a float, but you're now trying to interpret those bits as an integer.
And the consequence of that operation is, well, it's what's referred to as undefined behavior. We need to spend a moment on that phrase because it's genuinely terrifying in low-level programming.
Undefined behavior means the compiler is permitted to do anything. And that doesn't just mean it will crash. It might give you garbage data, or it might work perfectly for 10 years and then suddenly fail when a different piece of code is compiled with a slightly different optimization flag. In short, it means the result is unreliable, unpredictable. You lose all guarantees.
That unpredictability is why the manual tracking is such a heavy burden. The importance of this singular active member rule is what makes the memory sharing possible, but it forces the programmer to meticulously track which type they last stored, usually with some, external variable. If you could have two active members, you just have a struct. You need two memory locations, and that defeats the entire purpose.
And this leads us directly to the significant limitations that really reinforce its specialized role. Because the language has to maintain this tight control over the memory layout and guarantee its size, it imposes very strict constraints on what can be a member.
Okay, so what are those specific constraints?
Only primitive types are allowed as members. So these are the basic, tightly defined types that C and C++ inherit. Things like char, int, float, and double. Types that have a standardized fixed size that's known definitively at compile time.
So any complexity is explicitly forbidden here. I can't put a standard library string or a large multifaceted structure. I define myself inside a union.
Precisely. User-defined compound types, like a modern dynamically allocated string or other complex structs, are explicitly not allowed as a member. This is a crucial point for anyone learning this.
Why is that restriction so absolute? Can you connect that back to the memory-saving goal and that fixed size requirement?
Yeah, sure. The union relies entirely on knowing the maximum size at compile time to allocate that single dedicated chunk of memory. A modern std.string in C++A, for instance, isn't just a simple sequence of characters. It's got hidden pointers to memory on the heap. It has length variables, capacity variables. If you put that inside a union, the memory allocator for the union itself becomes meaningless. The string's actual data is living somewhere else, and it's dynamically changing its size.
So if the language allowed a dynamically sized type inside a union, the whole size guarantee would be violated. It would involve heap allocations and pointer management, and that just instantly breaks the whole low-level, high-efficiency design principle. It destroys the union's identity as a fixed memory saver. It's just too complex, too unpredictable for the kind of bare metal optimization unions are designed for.
Exactly. The union forces programmers back to first principles, work within the confines of fixed-size data. It's a tool for specific tasks where you need that bare metal efficiency and where the language passes all responsibility for data integrity to you, the programmer.
Okay, so now let's pivot to the so what of all this. If we connect this back to the bigger picture, given all this complexity, all this risk of undefined behavior, why would anyone use this today? The sources note that union types have limited and very specific applications in the real world. They are definitely not a general-purpose solution.
No, you would never use this for, say, defining a list of customer records. You use a union when the memory cost of a standard structure is truly prohibitive. Or, and this is a key point, when you need a highly technical, efficient way to treat the same sequence of bits as different data types. This is called type punning, and unions are the primary, safer way to do it in C.
The primary use case, explicitly highlighted in the sources, is saving memory, especially in highly constrained environments. But I think the most illustrative example comes from network programming.
Right. Let's use a concrete industry context. Network applications for serializing and deserializing data. Imagine a protocol where the first 64 bits of a network packet could represent one of two things. Either a very large 64-bit encryption key, or R, a timestamp represented by a 64-bit double precision float.
Okay, so a standard struct would require 128 bits. 64 for the key, and another 64 for the timestamp, even though only one is ever present in any given packet.
Exactly. By using a union, you define a single 64-bit space. When you're writing a key, you write to the key member. When you're writing a timestamp, you write to the float member. You just saved half the bandwidth for that segment in every single packet you transmit. That optimization scales exponentially in high-volume, high-speed network traffic.
That makes the trade-off worth the risk. You are intentionally optimizing for bandwidth and speed. But that brings us back to the safety issue. How do programmers manage the inherent danger of that singular active member rule in professional environments? They can't just rely on, hoping they remember.
And this is where we introduce the crucial modern refinement. Tag unions or variants. This is the key insight into how the concept is used safely today, often in languages like Rust or even in advanced C++ libraries.
Explain that. What's the mechanism of a tagged union?
A tag union is not just the union itself. It's a standard struct that contains two things. First, the actual union of data types, and second, an external field, a standard int or enum, which we call the tag.
So the external field does the bookkeeping for the dangerous memory sharing union.
Precisely. The tag explicitly tells the program which member of the union is currently active and valid. So before accessing the data, the program checks the tag. If the tag says ID, the program knows it's safe to access the int member. If the tag says time, it knows it's safe to access the float member.
So the tag union basically formalizes that manual tracking step that C originally forced onto the programmer. It wraps the low-level efficiency of the union with the high-level safety of a standard structure. That immediately makes the concept palatable in a modern, safety-conscious code base.
That is the evolution of the idea. It lets you leverage the extreme memory economy of the union without the constant threat of undefined behavior. But even with that elegant solution, the practical context check from the sources is still valid. Using a union is not a strict requirement to solve many general programming challenges.
That reinforces that even with a tag, this is still a highly specialized tool. If you're solving a standard business problem and you find yourself writing a complex tagged union, you should probably pause. You should check if a standard class or structure could handle the task more safely and readably without that level of optimization. Readability and safety, they often trump hyper-efficiency unless you're in those highly constrained environments, like embedded systems or high-frequency trading platforms.
Exactly. But understanding these specialized tools, even if you rarely use them, it completes the picture of efficient programming design. You learn about the foundational trade-offs that have governed computing architecture for decades.
So let's summarize the three core things the listener should really internalize from this deep dive into the land of ultimate efficiency.
First, internalize the definition of a union. It's a memory-sharing, user-defined type, borrowed from C, designed to store different data types into the exact same memory block. And that block is only allocated for the size of its largest member.
Second, remember the core risk and the constraints. Only one member can be active at a time, and only simple, primitive, fixed-size types are allowed. Violating that active member rule leads you directly into the danger zone of undefined behavior.
And finally, recognize the application. While it's dangerous raw, the concept is used safely today in structures called tag unions. They allow programmers to save memory and bandwidth in very specific contexts, like networking and embedded systems, while mitigating that catastrophic risk of confusion.
It fundamentally changes the way you view memory allocation. It forces you to respect every single bit of allocated space. Which brings us to our final thought for you to chew on. If maximizing speed and minimizing memory forces language designers to create specialized structures like unions, where the programmer has to explicitly manage which variable is currently valid, what other surprising and complex design choices exist at the hardware level, in the chips themselves? Choices specifically intended to push the boundaries of memory and speed by forcing a similar kind of resource compromise.
Think about the design of specific CPU registers, or concepts like bit fields, which push this idea of efficiency even further down to the individual bit level. If you want to explore the ultimate technical deep dive on this, looking up the specification for C's bit fields is a fascinating rabbit hole that really extends this very conversation.
We hope you now feel dangerous in the most low-level, efficient way possible. That's it for this deep dive into union types. We'll catch you on the next time.